Okay, my name's Jim. I work on MicroPython, work for Damien doing MicroPython development, and one of the things that's come up quite a lot in talking to people about MicroPython, and my background before this was teaching MicroPython to school students, is issues with the garbage collector. And so being an interpreted language, garbage collection is a big part of how Python works, and there's some fairly unique challenges that are associated with running it on a microcontroller. Feel free to jump in any time, ask questions. I'm just going to cover a few highlights and then go into some details about how it works under the hood. This is probably very basic, but on a microcontroller, RAM is just an array of bytes. There's no on the sort of things that we run MicroPython on. There's often no MMU or anything sophisticated, and we pretty much get to say RAM, all of memory is some number from 0 to the maximum addressable spot, and then the actual SRAM will fit into some region of that. And MicroPython is given pretty much free reign of that. Other areas will be things like memory mapped I/O, or mapped flash or something like that on an ASP32. But we take the whole area, and we configure the linker script to say that the heap runs from, say, here to here, and then we check the stack at the end, whatever order you do it, doesn't matter. And then we'll have something like data and BSS. So in your C program, any things that you create with a global variables and not on the stack will be allocated space in memory by the compiler. Then everything else is left over for us in this area. We call it a heap. Now, if you're writing C, you'd be managing that with malloc, and so there's code in your program that's linked into your program that when you call malloc, goes and finds some chunk of the heap. So if I want 100 bytes for some purpose, it goes and finds 100 bytes free in here somewhere and gives it back and returns that as a pointer. And then I'm responsible later to say, I'm done with this pointer, you can mark that as free now, and it's available for somebody else. And maybe someone else comes along later and they need 200 bytes, and it turns out the adjacent 100 bytes were also free, and so that now becomes a 200 byte allocation or something like that. Somewhere, malloc has to keep track of what was allocated and what was free. But it's a very, very simple job. It just has to say, don't ever hand that out to somebody else, but I'll assume that when you come back, and I just mark it as free. In a garbage collector, we get rid of that second half. We never have the corresponding free. The program is responsible, and the low-level parts of the program are responsible instead for figuring out when we're no longer using that pointer. And the way we do that is we have to have some way of identifying what counts as being a pointer in use. And in MicroPython, we do this with most garbage collector languages. We do this thing called root pointers. So root pointers are a small collection of pointers in our program from which, if I traverse that in a tree, I'll find every other thing that's active in the program. One simple example of this is in MicroPython, the program, all the globals in the program are themselves root pointers. So when I create a global, I get a MicroPython prompt. So they're not actually technically root pointers, but they're a good example in terms of a pointer that I would follow to find other things. So if I create A as a string, hello, then this thing I have that's A is a global variable now. And if I looked at the collection of all globals, I would find all the things that they reference. And if those things were complicated objects like classes that had other members that point to other things, I could keep walking them to find that. But the problem is I want this to work with both Python objects and with objects that are written in C. So if I have some struct in C that has a member that is itself a pointer, or maybe it's an array, and some element of that array is a pointer to something else, I need to find all of those things to make sure that those parts of the heap are kept active. Because the goal at the end of this is to find out which parts of the heap are no longer active, so that I can mark them as free and give them back out in subsequent applications. So the source of root pointers is things like port specific, so maybe peripherals, things like if I create an instance of the Bluetooth class, there's a global Bluetooth class once I create it, and then the port remembers that for ports that support Bluetooth, that Bluetooth was initialized, and therefore I have to remember to search it for more things. So in Python I had a callback onto the Bluetooth, so when data arrives from the Bluetooth, that callback is now referenced from that Bluetooth pointer. Callback might have itself some variables that it was a closure around, or it might have some scope, something like that. I also searched the stack, the C stack, and I also searched the CPU registers. So this means that if I'm in the middle of doing some code in C where I've like just allocated some data or something like that, and then the garbage collector runs, because it might interrupt, but I haven't managed to stash that pointer anywhere in a structure that's findable by a root pointer, it'll still be findable because it's currently sitting in a CPU register. So the port provides how MicroPython discovers all of this. But I haven't answered the question yet, is how do I know that a pointer is active? And the answer is that if I search all of memory and I look at every single 32-bit word in memory, so on something like on an STM32, you've got 100 kilobytes of RAM or something like that, we walk through every 4 bytes of that RAM and we look at it and say, do you look like you're pointing to something in the heap? Yes, no, maybe? Maybe turns out, or yes or maybe, which turns out is that do you point to a heap block, which we'll come to in a second. But the point here is that MicroPython's garbage collector is precise. It's not precise, but it will never make a mistake. So it'll never assume something isn't a pointer, but it will sometimes assume things that are
so false positives.
False positives, yeah. So it might say that that is a pointer when it isn't, and it might therefore mark a section of the heap as active, but it will never accidentally think that a part of the heap is inactive when it is. So the way the MicroPython garbage collector works is it divides the heap up into four word blocks, and then all allocations are rounded to the nearest 4-word block. And this is actually really, really important for writing memory efficient MicroPython code, because no matter what you allocate, it will always be rounded to 4 words, which on most MicroPython ports is 16 bytes. So you could be very carefully making a byte array that is exactly the right number of bytes, but it will be rounded up to the nearest 16. And it would be really nice if it didn't do that, but the reason you'll see in a second is that we want to manage things in terms of allocations. It's much easier if we have fewer things that we have to manage. So by partitioning memory up into slightly larger blocks, and if those blocks are regularly spaced, then we can manage fewer things. So this slightly also improves looking through everything and seeing if it looks like a value that happens to point at the heap, because it must always also point to the start of a block. So it must round to 16 bytes. And also, if your allocation is larger than 16 bytes, we mark the head of the allocation separately from the tail. So it must also point to a head. But that's it, basically, in terms of how complicated the garbage collector is walk through all of memory, starting at the root pointers, follow this tree. Anytime I see a pointer, mark that block as active, and then walk through memory word by word. And if I find anything in there that isn't recorded from that previous phase, I then mark that region as free, those blocks as free. Now, this means that you do occasionally see some very surprising things where people have memory, they run GC collect and nothing gets collected, or not enough gets collected, or whatever. And that is a side effect of if you just happen to have numbers in your code that were the right numbers. I've only seen this like once or twice, and I think it's the sort of thing that if you ran the program again, you wouldn't see it again. The other thing is that we somehow have to keep track of what the state of all these blocks are. So I lied a bit earlier. The heap is not really starting at the very beginning. There's a section on the beginning called the Allocation Table, and the Allocation Table is as big as it needs to be for as many blocks as we're going to fill the rest of the heap with. And it's 2 bits per block. So you can think of one allocation table byte, which in the code we refer to as an ATB. So an allocation table byte is 8 bits, of which they come in pairs, and so it's byte gives you 4 blocks worth of information, and it's 0, 0, 0, 1, 0, 1, 1. So that's a free block. That's a head block, I think. Tail and mark. So we can look at this data structure to see what the state of the entire heap is, and so an allocation therefore comes down to searching this bitmap for a contiguous run of zeros that is the size of the allocation we need. So if I'm trying to do a 160 byte alloc, I need 10 blocks, so I need to find, this is contiguous on either side, but I need to therefore find 2.5 bytes worth of zeros, 5 bytes worth of zeros, no, 2.5 bytes worth of zeros to satisfy my allocation. And this is now the most important performance thing, is that somehow I'm searching this bitmap every time I do an allocation in MicroPython to find contiguous runs of zeros that I can then turn into head and tail markers. That can be slow because it's a lot of memory that we potentially have to search. And as the heap grows and as the heap gets fuller, the likelihood of finding contiguous runs of zeros is decreased. And one of the more common sources of memory errors in programs, like the program runs for a little while and then suddenly starts running out of memory, is fragmentation. And so if my heap gets filled up with allocations and then some of them get freed, some of them get collected, but I leave gaps behind, then I'm going to have a harder time making contiguous allocations. So let's say this represents memory, the heap, and when I cross out sections, that's an allocation. So maybe I allocate a whole bunch of things. Then a collection happens because I've run out of memory, and the collection finds some things that are free. So I make some bits free again. And then later in my program, I want to do an allocation that's like this wide. And there's actually that much RAM free, but not in one contiguous one. So it's very important that the garbage collector doesn't leave gaps in memory, which is possible. So more sophisticated garbage collectors, like in big languages, have the ability to compact the heap or defrag the heap. But that comes at an incredibly large overhead. The simple way that process works is that if I want to compact the heap, I have to be able to move memory around. If I want to move this chunk of memory here, so let's say I want to move that one to there to make a bigger chunk, anything that pointed to that needs to be updated to say here's the new address. But as we discussed in earlier in MicroPython, we know that a thing is probably a pointer. We don't know it's definitely a pointer. And so we can't go and change it because it might actually just be your temperature sensor's value or something like that. And the way you fix that, of course, in a more sophisticated garbage collector is you would have additional metadata tracking which things are pointers, and access to pointers would go through some level of indirection. But that's really expensive and takes a lot of RAM. So MicroPython doesn't do that, at least for now, unless somebody can come up with something very, very clever. So what causes fragmentation? Why would a program allocate in a pattern that looks like this? And the most common, but this is a slightly unfair thing, but there's sort of an exaggerated example, is a program of the form some sort of while loop, more true, do a whole lot of work to calculate a result, and then I have a list, data something is a list, and then I push I go data.append result. And so what happens is I end up allocating a whole lot of blocks to do this work, and then one thing of that calculation I then saved into my array. And so as this program runs, it goes work, allocate a result, and then push it into the list. Let's say the list was already allocated back here, so that this is an allocation for the list, but it's internally it's growing and getting filled up. And then I work, allocate the result, add it to the list, and then the collection happens, and then all of this gets freed, and that's the result in the end, and I leave these behind. And so now I'll never be able to do once that program is run until the end of heap, and the first collection is run, I'll never be able to do an allocation in the future bigger than this. And that might not be a problem if my program is completely deterministic and consistent. But if I'm doing something like a web server and I'm getting variable length requests from users or something like that, I might have taken a whole lot of very small requests, and then now I get a really big request, and that big request will not fit in memory. So this seemingly innocent thing, you know, keeping some statistics or remembering my last 20 times that it took to process a request or something, that could be something really, really small. It just has to be something that I've left behind in memory. It's obviously particularly bad if the requests are variable sized. So how would I fix that? It's actually really tricky to improve on this, and it's an issue of the way garbage collectors work. One thing to do is to make sure that the thing that you're storing doesn't actually itself have to be on the heap. So data is a list, and the way lists work in MicroPython and pretty much every language is that we allocate bigger than we need, and we fill in the slots inside that allocation. A very small number of things in MicroPython themselves can fit into, I should explain something else. So fundamentally in MicroPython everything is an object, an MP object. And an MP object is either a pointer, a small integer, or a small number of built-in things like true and false, and on some ports some floating point values, or a string value. So none of those things live on the heap. They don't have to live. They don't have to continue to live on the heap. They can be stored in the list directly. Whereas everything else that's allocated would have to be the item in the list as a pointer to the allocated object. So if all I was doing was calculating a number, then if this was a number rather than a floating point number, then I wouldn't have this. So one thing you could do, if the example I gave earlier was to calculate statistics, if the thing I was saving in my operation was like time taken in seconds, floating point seconds, but instead I stored it as time taken in integer milliseconds, then the thing I'm putting in my list doesn't have to point to the heap, it is in the list itself. Simple improvement. Similarly, if I worked in integers rather than in floating point, there would be no allocations happening in here, so I'd actually be putting less pressure on the heap as I went along anyway. Does anyone have just pause and say a question on that? Yeah.
Do we have any visibility into how this is progressing?
Yeah, I'll show you. That's who I've got this from. So I have a PyBoard 1.1 running here. The two main interesting ways to look at what the heap is doing is through the GC module and through the MicroPython module. So GC has a bunch of useful methods. You can force a collection, which we're going to talk about in a second as an interesting way of avoiding fragmentation. But we can learn a little bit about the state of memory. So gc.mem alloc and gc.mem free. So mem alloc and mem free is measured in bytes, and it's basically of all of the bytes in the heap, once I take out the allocation table, how many bytes are available for allocation and how many bytes are free for allocation and how many are currently allocated. So that lets me track just how much I'm using. When that free number gets to 0, it forces a collection automatically. The other thing is import MicroPython. And MicroPython has a .meminfo function. And this tells us in total, this number should look a lot like the sum of those two numbers. So the total bytes is the sum of the allocated bytes and the free bytes. Obviously they won't match exactly now because I've used some heap in between. And this is an important way of looking at fragmentation because this tells us in the bytes that we've used, how many of them came from single block allocations and how many of them came from multiple block allocations.
Multiple meaning a head and tail.
Yeah, head and tail or multiple. Yeah, like head and tail, yeah. And so some objects that were like floating point numbers, they fit into a single block, but and complex number would fit into a single block, except on PyBoard SF6, where you're using double floating point, and it now takes 2 blocks because they're 64-bit each. So there's some interesting things there now that suddenly a complex number on when you have double enabled takes up twice as much max block size and max free size. So yeah, but the more interesting version of this is MicroPython.meminfo. If you pass any argument to meminfo, it actually dumps the heap. So just make it slightly smaller. So same information to start with. It tells us where in the address space the heap is located, but then it's telling us what is that. Each one of these characters is a block. So this is a head, and it's a 2-byte allocation. So it's a head with one tail, and then a single block, single block, single block, single block, and then a really large allocation. I don't know what that would be. And then sometimes for certain types, it can tell us what type of the allocation is. So this B here is a single block. B is for bytes. Yeah, byte array. Yeah, something like that. String would be here. Yeah. So this is a single byte string. Sorry, single block, I should say. So a short string, shorter than 16 bytes.
B is a function, bytecode function.
B is a bytecode function. So that would be some code that's been evaluated on the REPL or something. Maybe have a main.py. This is probably this is possibly the text of main.py or the program of main.py or something like that. But notice there's no fragmentation going on here. There's no dots in my allocations, except for a very small number of them. And now what's happened here is that the MicroPython firmware can explicitly tell the heap that it's done with a pointer, in which case it marks that as free preemptively. But for the most part, because I've not run a collection, there are no free blocks. So if I now run GC get collect, and then that same output, you'll see some of the things were left behind, but a lot of things were freed up in between. And if we were to overlay these two things on top of each other, what's happened is that some of them have just become free. And what's happened here is that everything I've done on the REPL has probably resulted in actually. I'd have to, yeah, you have to spend a bit of time looking at what your program does and why this thing. But what we've already seen is that we've got a fair bit of fragmentation going on in a small way, and if we continue that throughout the whole program, we'd probably do anything. The REPL's a bit of a hard way to measure this because everything I'm doing is at global scope. So every variable I create is there forever and behind.
It's evenly spaced. Like on the whiteboard, you've got at the bottom here, you've got some dots
Yeah.
showing evenly spaced. Is that because every allocation starts searching at the start and then just goes forward?
I was just about to, yeah.
So is there no other plan of going back-
That's
searching
coming up very
backwards
soon.
or-
Yep, exactly. Before I come to that, does anyone have questions on this display as well? This is one of those ones where it's pretty intimidating the first time you look at it, but with a bit of looking at what your program does, and in particular watching how it changes as you use the REPL, for example. So I just did a soft reset, so it's reset the heap back to the start. So to answer your question though, at the very beginning of that, it remembers where the last single byte allocation succeeded. The theory being is that there should be no free blocks to the left of that earlier in the heap than that. So we should expect that allocations will start from here because this was probably came from a free. But if I now say A is equal to a really long string, so long enough to not be a Q-stra. Oh no, actually probably. Q-stras are really complicated. Strings get turned into blocks, and then the blocks get allocated on the heap as well. I'll just make a byte array. 100 bytes. And I look at them heap. I should see my byte array. So I made that was likely it. 1, 2, 7, 16. Big enough. Yeah, probably it. And
Yes.
if I keep doing this, you'll see my heap will fill up with a whole bunch of these glider allocations. And if I now run collect, just the last one will be left, and all those other ones will be cleared out. That's the ideal case of nothing from here to here needed to be kept. But this brings on an interesting point. When I write this line, a is equal to, so I'm creating a 100 byte array. Actually, what I'll do, GCDogs free. So I should be able to write a is equal to byte array that's like 70,000 bytes long, because I've got 100,000 bytes free. But I can't then do this, despite the fact that an allocation, if I did now, if I did a small allocation, like 15,000, that big allocation is long gone. It's when I've tried to do these small allocations, it will have gone and said, oh, this old one is no longer referenced, I can do a collection, clear it up.
So Jim,
Yep.
you mentioned it in passing before. Are you saying that when it runs out of free memory, a garbage collection happens?
Forces a collection synchronously, immediately, yeah. So synchronously in the sense that it runs right now and blocks until it's finished.
Okay.
And immediately in that, that's kind of implied by synchronously as well. When I run GC.collect here as well, it runs immediately then as well. So what would have happened here is that would have worked, that would have worked, possibly that one maybe, and then this one would have said, oh, there's not 1500 bytes free, I run a collection, and all of that got freed, and now I had an allocation I could do. And my program could do that in a while loop forever, and it would just keep walking through the heap and collecting every few allocations.
Yep.
Sorry, I went up too far. Sorry. Not what you want to do. But what I can't do is that, surprisingly,
Because the gaps are too small now.
because no, it probably isn't that the gaps are too small, but the problem is that probably that 15,000. So this is my. Oh, wrong.
Can you show us with that other command?
Oh yeah, that's a good idea. That's a great idea. I can, but what we're seeing here, so the layout does this cool trick where it hides the hidden lines. But notice what's going on here. We've got a bit of stuff at the start, 57 lines, so that's
57K.
it's 1024. Yep, awesome, good feature. 57K of free memory, and then here it starts the 15,000 byte allocation, and finishes here, and then another 23K free data. So I've got 100K of RAM, 57K free, 15K used, and then 23K free. I should have room to allocate 70K because I've got that much free RAM. But the problem is if this is total memory, total heap, I've got 15K stupidly sitting here, and I can't have a 70K either side of it. But more importantly, so that is a problem on its own, and there's no workaround for that. If you've got something allocated here, that's like fragmentation in its simplest possible form, a single allocation. I mean, I could have a single block allocated here, and I wouldn't be able to allocate 55K either side of it. But what happened here was that I did this, and I allocated that 15 kilobytes to A, and then I tried to do a 70K allocation. Even though that 15K allocation is no longer needed, it's needed right up until the moment that I allocate the result of this back to A. And so this is actually, probably if we walk away from this talk with one thing, if your code does the same variable over and over again, that variable doesn't become available for collection until after the subsequent assignment to it has succeeded. So there's a few ways around this, but if your code is getting memory errors because loops and whatever, the likely thing is scope is lasting for longer than it needs to around a collection. So the simple answer to this is if I just write A is equal to none, then I can happily do my 70k allocation. And what you'll see is that it chucked the 70k somewhere. I don't know. Oh, right at the start. That was really nice of it. Because it probably did a collection and then everything was free and the pointer was reset. So strategic use of making sure that variables are no longer in scope and explicitly running a collection can force the heap to be in a really good state. So what we did there is we cleared A, so it was no longer pointing to anything, and then immediately collected, which brought the pointer back to the start, and then we have the whole heap to work with. I wrote A is equals to none because it's clear as what's going on here, but the same thing is true as if I'd written del A, which actually just clears the A variable altogether from scope. So now A is not defined. Has the same effect.
So it's a good practice then to just delete variables you don't need anymore in your code and not leave it for the garbage collection to do. Won't it be quicker for the garbage collection to run?
Yeah, almost in all cases. Don't try and mess with this. It's like when you I don't really have a good specific one size fits all advice here because I would hate to see everyone just putting dells throughout their code willy nilly to hope that cargo cult their way through this. The classic case is something like
Just before big allocation.
yeah, exactly. I'm reusing this variable for something. I don't know if this is the problem, but a story that I heard recently, I have a program that in a while loop does 6 web requests. And, and that's a totally normal thing to do. Like I'm checking some site or I'm getting some data or whatever. And it seems reasonable to me. I don't, like, if I were to write this program, I would write something like request is equal to uRequest.fetch.post or whatever, and put the URL in here and store it in the request object. And then I do a little bit of stuff with the request. And then immediately the next line I was like, okay, next thing to do, request is equal to, and I might even do something cool, like make that a function, like, handle rec or something like that. And then I do the same thing, the next URL, and then I handle that one or whatever, different function maybe. But I've just fallen for that trap, which is that this has to stay in memory until this entire HTTP request has succeeded and allocated. And if this was something like fetching a JSON URL or something like that, then in memory I have the raw data that came back plus the object that came as a result of parsing the JSON or something like that. So this has to do quite a lot of allocations while still holding on to the old from this one. I forget the internals of your request, but I don't know if it holds on to the text and the JSON if you only use the JSON. I think it holds both. So a strategic del request here would help. But the simpler way, and to answer Sion's question, probably if I were to try and make this into one piece of advice, when a function goes out of scope, all local variables of that function are now out of scope, obviously. And so the more you use functions, the more this problem is less likely to bite you. So if each of these was a function that I called, let's say def handle URL or something like that, and it took the URL, and then it does rec equals whatever, and then it returns. Let's say I wanted to fetch like a single number from this URL, but I had to parse a megabyte of JSON to do it or something because it's 2020 and that's what I do. But I want to return a number. Foo.foo.foo.foo.foo of some property.
Also, the status code.
The status code, yeah, sure. And then when that function goes out of scope, request goes out of scope, is immediately available for collection or something like that. So, in general, I think I would advise put stuff into small functions and then you don't have to worry about it so much. And also not doing it at global scope. If your main program had the while loop up here, you could put the whole thing into a main function or something like that. That might help you. Was that the question you asked? Was I think you asked a different question? So,
I was asking about like the periodic sort of small allocations you've got.
yes, and then it resets back to the start.
Is caused by every time you allocate, you always start and scan forward looking for something.
Yep.
Whereas if you were scanning forward and then maybe back or
Yep.
different plans on how it scans for new allocations, the overall fragmentation might be very different.
Yep, absolutely. So it's very important to avoid fragmentation, and there are lots of things that we could do that would make everything a lot faster if we didn't care about fragmentation. So one thing would be never ever try and scan where we think there are used blocks. So don't go back to the start, for example. Always walk forward, but then you would maximally fragment. So the trade-off that MicroPython makes is that it has this kind of assertion that it will never move the search point. So let's say this is the heap, and here is the current search point. So I think it's called last free alloc or something, or last free book or something like that. And the invariant is that there's never anything to the left of that is a single block free. There's never a block free to the left of that. That's the idea. So the way that is enforced is that this pointer will only be advanced during a single block allocation, and anytime we do a free, so some parts of the code do frees explicitly, it will always move this back. If the free happened earlier in the heap than where the current pointer is. So it's always trying its hardest to keep that to keep everything filled leftwards. But there's an interesting thing you can enable, which is the threshold. So I don't know do any ports enable the threshold by default? Sorry, but so there's a feature. So what I said earlier is when an allocation fails, and it's a collection, but you can say if the heap ever gets more than a certain amount full, then trigger the collection early. And so that kind of puts a little bit of pressure to keep more stuff free at the end, and more pressure for allocations to happen earlier in the heap, at the expense of that you probably will never be able to use all of your, because you'll be always collecting earlier. And you'll be collecting more often, which is slow. But strategically, what was sort of expanding on what I said earlier, by being very careful about when you call collection, you can have a lot of control over where this happens. So if your program is always allocating in a loop, for example, so if we go back to that one earlier, so it's while true, do a bunch of calculations and work, calculate some result, stash it in the list, so that data list that is growing. And then so I'm going to append it here. Now, if I don't want to do a GC collect here, because a whole lot of stuff here is still in scope, but if I maybe did it at the start of the loop instead, then I'm always resetting the pointer back to the start, and the previous set of junk that is now left behind will be cleared. And the result of this is that I'll always be working kind of, I can kind of draw it. So let's say this is the start of the heap. I'll alloc for the work, and then this is the thing I'm keeping, and then I immediately start again, and I GC collect this, and then I maybe do alloc, and then the next one was a bit smaller, so it gets the thing that's the system gets stored here. And then I reset it at the start of the thing, reset again. And then maybe this is a big request, and it does a lot more work to figure it out, and it gets stored there, and then I collect again. And so I'm still going to end up in this situation where I'm creating isolated blocks, but overall they're a lot more tightly clustered together than previously when they were spread out through the heap. And if I do occasionally have a thing where I need to suddenly allocate, a really wide block, then there'll be all this space out here for me to do that. And I can watch, the way I would do that is the program would do something like MicroPython info 1, like I was doing earlier. After each allocation, you could see how the heap grew. What you basically want to see is that the last line where it says how many lines are free at the end, you want that to stay big. Okay, more questions?
So based on what you said before about that last free thing,
Yep.
Obviously, and as you mentioned earlier before this talk, especially with PSRAM or SP32,
Yeah.
the bigger the RAM, the slower it all works because you've got so much memory to traverse, right?
Yeah.
So, where is there a sweet spot where, as you fill up more memory, things become faster?
Yeah.
Like if they're not clearing previously, like if it's not, like if a lot of it's staying intact.
I think it's hard to give a general answer here. It's again, you have to measure it out and do some analysis. So to reiterate what Sion's saying there, the cost of doing a collection grows with two things. the number of things in the tree that I have to visit to find out what's active, and then secondly, the amount of total memory I have so that I can find everything else that's now I can convert to free. And so those things don't necessarily grow at the same rate. And so there's a trade-off. There will be a sweet spot for any given memory configuration and program which sets the optimal rate to be doing your GC collections. And the answer is probably not automatic GC collections.
Right.
Probably you're better off doing manual collections at some point. Would you agree with that? That like if you really wanted to make a high performance app, you'd be, certainly in my experience. But
I mean, every time you do a GC scan, it has to scan through the whole heap,
yeah.
regardless of how much you use or not.
But so it's not doing it based on that last known pointer? That's only for allocating, not for scanning. Right, okay.
And we've talked about how could you
Scanning
do
goes
it.
back to the start.
Yeah, right.
Could you do like short collections and only collect leftwards of the pointer or something like that? I haven't come up with a way that works yet.
So what about giving us away? I know some bad idea. But like, I think what you were implying
That's what I was about to say.
before was, why not, that you were talking about clearing and reusing that thing and clustering it, why not switch ends? Why not give us the ability to say, okay, I'm about to spam, I need to do this loop 100 times, right? And I know I'm going to do that, and this is optimal as I can get my allocations. Let me allocate this chunk from the end of my heap.
Yep. And so now we're moving on to like future thoughts, future directions, and this is a great example. Like most things in where the computer does the work for you, the computer will do better with more information. And one really key piece of information that would make a difference here is when it does an allocation, is this going to be an allocation that lives for a long time or for a short time? And I think that ties into kind of what you're saying, which is that if I can tell it more about the allocation I'm about to do, whether it's how long it's going to live for, or whether or not it should be done earlier in the heap or later in the heap or whatever, that would certainly help it.
So some type of hinting system.
Yeah, and this is a thing that CircuitPython has. I'm a little bit fuzzy my memory on the details, but CircuitPython does have effectively 2 pointers, so it has 2 versions of this pointer. And certain allocations can be tagged to go to the. Now, this is from memory. I'm not exactly sure what the details are, but it's something along these lines. And the idea is that it can, as much as possible, put long-lived allocations elsewhere in heap, so that the short-lived allocations all get cleared together. You don't leave things behind. But that requires, the way it works at the moment is they do things like when you do a module import, the bytecode will be obviously a long-lived allocation because you can't unimport a module. You can't. Likely you don't import a module. Yes. Potential there for improvement? Yeah,
So
definitely.
would that be something like allocating an extra argument to say long-lived, short-lived?
Yeah. The problem where this gets hard is that you don't call alloc in Python, obviously.
Yeah.
You'd have to somehow say, I'm about to do this alloc or something like that.
Pre-malloc.
Yeah. And the other way of looking at this problem is, well, maybe the GC could just do a better job of watching what your program does. And this is a hugely successful area of interpreted language, things like JITs and tracing VMs and stuff like that. They watch what your program does over time and figures out what the way they optimize it for you based on usage patterns. And so if it could say, hey, this is while loop, and every loop you do this collection, friggin' hell you leave crap behind on the heap, this one thing. I'll just remember which line of bytecode that allocation came from and something like that. But more RAM, more time, all of these things. It's a very,
But
very
couldn't you just
delicate trade-off.
make some assumptions though? Like if you've got just generally stuff in a tight loop,
Yeah.
right? And you should be like, that's a while true, right? So sure you can break out of a while true, but you can, like there must be some assumptions MicroPython can make.
Yeah, I'm sure there are wins here, absolutely. And like I say, this is a tremendously successful area of computer science.
Scan forward and look forward.
And
Well, you wouldn't even need to. That's what I'm saying. Like if it's in a tight loop, it's running over X many times to infinite number of times, then the assumption is going to be that they're going to be small allocations.
As
that
always,
you could probably.
and maybe the last bit, yeah. As always with MicroPython, of course, the trade-off though is that this all just the more even simple stats, So as a simple example, what I tried to do is try to keep multiple pointers for different size classes. So the idea is that the single block Alex went to this pointer, 2 block, 4 block, 8 block, etc. And that helped. Solved a whole class of problems, made a whole class of other things slower. And so I think one thing to definitely look at is before going into much of this, like quantifying the performance of the collector and quantifying fragmentation, I think is a really useful exercise. So we can actually conclusively say we made this improvement to the GC, we had fragmentation tests and they got better or something like that.
Fragment? Oh, sorry.
Would there be some way that we could get the program to participate in the fragmentation?
Yeah.
Like something you can
Potentially,
call and
yeah.
say, here's a list of variables that could be reallocated.
Yeah,
or the memory could be moved on these, and your program participates in that defragmentation process.
Yep. I'd like an option that said, hey, I promise I'm not going to have any numbers that correspond with the values in the heap. And then you can assume that it's 100% precise and do defragmentation or something like that. And that's an extreme example, but like you could opt into to making your program more. At the end of the day, like, it's like if you've got 4 megs of PS RAM, who cares about any of this? But if you're on a smaller micro, in L0 or something like that,
So you've got more levels of abstraction between what the heaps keep track of and what the user's using.
yeah.
If there's an abstraction in there, you can then remap memory.
There's a lot
But
of
if there's none,
there's a lot of information
the
lost.
program would
in
need
that.
to then participate in some sort of.
And it just costs. If you have to pay an extra couple of bytes per pointer, it's not even worth thinking about that. So one thing I've been looking at recently, I don't know if I'll ever be able to turn this into a viable PR, but is making that searching cheaper. There are I think a lot of programs that come up with an issue where, because this pointer is so reticent to move to avoid fragmentation, you do often find the situation where every allocation actually has to search quite a lot to find the free allocation. The first sort of what made this interesting to me was there was a forum post where somebody was using complex numbers on the PyBoard SF6, so I mentioned this earlier, double precision floating point. And suddenly that means that every complex number is a 2-block allocation. And so all their program did was allocate complex numbers. And that meant that pointer never moved forward because they never did a single block allocation in their type.
So you have to keep searching from them all the time.
And so every computation, literally every multiplication they did created a new complex number on the heap and got n squared in the allocation time. And there's kind of not a good fix for that because you don't want to move the pointer, but maybe we can make searching faster. And so the thing I'm working on at the moment is allocation comes down to searching a bitmap for free zeros. And a simple observation is if you look at that byte, so it's in 4 pairs of 2, only one of those bits is actually indicating if it's free or not. The other bit is indicating whether it's a head or a tail. So by separating it instead into 2 tables, so this is the freeness, and this is the headness. And now you get the information density is twice as high. And so you can look for one memory access to get a byte of state, you can get twice as many blocks represented. And also, you can overall do a collection and then look at fewer bytes of RAM. And when you modify the state of a block, you're either changing it from free to allocated or from head to tail, and generally not both at the same time. So you actually do half the memory writes as well. And the other thing you can do is you can now start treating them as bytes and treat them as words instead, with some complexity. So the problem turns into find me free words that are just zeros. I don't care what their state is, I just care about a need of a 0. And CPUs have this, a lot of ARM CPUs, well, all the ARM CPUs that MicroPython deals with, and a lot of other chips as well, have a CLZ instruction, which is count the leading zeros of a word. And if you prefix that with an R bit, reverse the bits in a word, then this becomes count the trailing zeros. And so you can quite quickly ask a 32-bit number, how many zeros have you got? And that tells you how many blocks are free in front of you. And by doing tricks like this, you can make that search a lot quicker while still not having to risk moving the pointer around as much.
Wouldn't an easier, that sounds cool,
Yeah.
but wouldn't just a really simple way to solve that problem with the double word thing would be just have a rule that says, because you're allocating, right? You know, you could track what you've allocated the last few times, like it's been a single or a single byte or not, right?
Yes.
If I've allocated 5 times in a row and it hasn't been a single, just move my pointer to where that new thing is
Yes.
and sacrifice that.
This talk is having
potential
exactly
one
the
thing.
effect I wanted, actually.
Right.
It's not about teaching you garbage collector, it's about making you want to become garbage collection developers so that I don't have to do it.
Because at that point you don't care if you've missed a couple of single
I
bytes.
implemented exactly that and it makes it slower. And it's just like, and the problem is I don't know if that's okay or not, right? But it makes it quite a lot slower.
Because it's some. Why does
it
it
adds
make it
some
slower?
situations,
Because it
but
adds
all-
an if statement.
Garbage collect. Oh, and also doing it garbage collection is expensive. So you really want to limit. You really don't want to do garbage collection. You don't need to necessarily.
It's an
Right, but that pointer is the last place that there was a single byte allocated or free.
The best way to think of it is there are no free blocks to the left of it. It's kind of the most concise way to be able to represent it.
At the moment, yeah. But if you started skipping ahead because of any other reason, that means you're leaving stuff behind with your single byte things that you may never get to, or when it wraps around that.
No, but that's only for allocating.
Yeah.
Okay, like at some point. Okay, so the rule would be, for instance, if you're within the first third of the heap,
Yeah.
just skip ahead and stop. Because your cost of going through the
But
search.
that all these things, and any time that you hit a threshold like a third or a half or a tight loop, how tight, what, all those thresholds will work for some applications and break for others, or be slower for others. So trying to tune something to be general purpose.
To look at that in a more, I think you could be right, and I think that would be possibly a good change. But I have no way currently to say whether or not that is a good thing for everybody.
No,
that uses my
absolutely, yeah, for sure.
And so what I would actually, as well as actually making the GC faster, I think that's the more important goal here is how do we think about making changes to MicroPython, and outside of the GC in general, we're starting to look at these sort of big project-wide changes that are probably good for most people, but we actually don't always look at answers. So the perf tests are a really good thing that Damien added last year, which is we can make changes to the core and measure them across a whole range of boards, and it's a wide range of things. So I use that when I'm working on the GC, like do the perf tests so overall get faster or whatever.
Yeah.
And annoyingly, they almost never do,
But they don't get slower.
This is the closest I've got with the CLZ stuff. So this is what I've got. They usually get slower, yeah. ESP32 is crazy because you make like slight changes to the way the code is laid out, and everything just goes haywire. And
But that's specific to the ESP32 because it uses a shared cache between the
it's
code
much
and
easier
the
to do
RAM.
testing on Python.
Yeah, and that's been fixed with the new stuff. But I was going to ask before, because this brings up an interesting thing what Andrew just said. Like, so GC is slow, but it's not really, right? Having a fragmented state is way worse, I would think, for a lot of cases, than a cost-effective GC. And a fragmented state is going to force a GC anyway, right? So, again, it's not going to work for every situation, but wouldn't averting fragmentation as much as possible, which is really, there's no cost in averting fragmentation other than maybe losing some usable RAM until a GC, wouldn't that always end up being faster than not?
I completely agree. Yeah, I haven't come up with a really good way to make it possible for the program to express its wishes in a useful way that's also developer friendly, and it now means that you have code that won't run on CPython and things like that. I mean, maybe you can write some wrappers and stuff.
Right.
Yes, you're 100% right, and whether or not it's automatic analysis or it's developer hints or it's something more complicated.
Right.
I do think about it, and I haven't come up, but I would encourage all of you to think about it. I think is the answer. But also I like playing with this stuff. So. Yeah.
One thing which I remember reading about a while ago was to have an up, or not up, maybe even a size that a user can allocate.
Yeah.
That all small allocations from one end and large allocations at the other end. So if you know that you're going to be defining frame buffer lots of 64 power something allocations, you can allocate them from the top.
Yes.
and everything else.
This is the
small things from
CircuitPython. This is a CircuitPython approach, and they do that. I don't know that they express that they make that available to Python code, but they have some heuristics that say that these allocations are likely to be the big allocations, small allocations. Unfortunately, size is not necessarily a good indication of lifetime.
No.
But yeah, Java solves this with they have generational GC and stuff like that, so that requires defragmenting heap.
Another question: if you developing something that's got to run for 10 years without human intervention, unless you're very carefully decoding, I presume it is eventually going to could well fragment.
Your program won't suddenly fragment.
No, but
And if it will fragment, it'll be happening from the very first allocation onwards.
yes, just slowly.
And so I think spending time with this tool is extremely useful for kind of building confidence around that. If you add that and that is not changing, like obviously it's going to be slightly rearranging, but if for the most part, I wonder if perhaps something like adding a high watermark, like GC.highWatermark. Is that even a
This
thing?
threshold.
The threshold is to set the threshold, right? But where I'm going here is, if I could make my program monitor what is the highest address ever handed back by the GC, if I knew that never went above a certain amount in 1,000 runs,
Yeah.
why would that ever go above that ever again,
Because
right?
what I'm just thinking is to run on something that really has to run forever, is to periodically store machine state in the NVRAM and reset, recover to the same machine state and continue.
I've talked to people who've done that with RTC RAM, I think on a
Yeah, sure.
Yeah. I mean, there's no better garbage collection than the soft reset, that's for sure. But more questions? Great.
That was awesome.
Thank you very much.
Really cool. Yeah.
Thank you.
If you did want it to last a very long time, several years, wouldn't you then maybe even have something that is another level of abstraction so that it can defrag its own memory? It's in the whole language. That
We have the vast majority of it's inside a function that you exit every now and then, maintaining just a couple of interstate things, and you may get to that.
You know what they say, all problems can be solved with another layer of abstraction. Potentially, but that layer comes at a huge cost, and that's why MicroPython doesn't do it. And remember, with MicroPython, often it's not CPU time and performance; it's memory. It's your precious resource, and that does cost you so much.
You mentioned Java before. That's obviously Java's got so many layers of abstraction that can do things like that.
Yeah. Yes, exactly. And it's got this generational GC. Well, it's been a few years since I looked at this. I used to. My old job involved working with a team that did JVM optimization, and so Java is a compacting heap. But if an allocation survives multiple collections, multiple compactions, then it's moved to an entirely different heap. And that's the luxury you have when you can move an allocation around. And so you build this sort of tail of old allocations. But what you get on a big
lifetime of the objects.
Exactly. Surviving collection is a proxy for
If you
lifetime.
can add hinting into Python, add lifetime.
Yeah.
The
The
you
prob-
just
the
gotta
problem
track
is
that
that
somewhere.
The problem
If
is
you're
that the
on-
things are not necessarily Python objects. They could be embed TLS objects, or they could be some
Free
library
RTOS
that we
ones.
use. Free RTOS, stuff like that.
If you've got gigs of RAM, you can afford the extra overhead of tracking.
The other luxury you have on a big computer is an MMU. So you're not dealing with physical memory. You're abstracted. You've got a hardware abstraction, which is the best type of abstraction, and you can deal with it through virtual memory instead. You have this giant address space that you can map in different ways, and so it's all sorts of different things.
If you're running BMS on something like Cortex A5 with MMU,
Yeah.
how hard would it be to add use MMU for defragmentation?
Still hard.
Still hard,
Yeah.
still hard.
Yeah, it'd be nice to have a defragmenting garbage collector that you could hash define enable if you've got a board with lots of RAM
I
that
suppose
just by someone to write.
The
So-
trick-
MMU granularity is a big in your
Exactly. The trick that I've seen there is much more about you still have a small amount of RAM, but you have a really large virtual address space, and then therefore pointers can encode stuff. You can do more with your pointers, because even though, let's say you've got this big virtual address space, it's all just repeatedly all pointing back to the same small physical space, but this pointer is still a distinct number to that pointer, despite them actually being the same pointer. And so you can encode data in the pointer itself and stuff. And that's the sort of tricks people play. Alright. I'm going to stop now. Thank you, everyone.
Awesome.